Dear students, this session is regarding unbalanced three-phase, three-wire star connected. In a three-phase, four-wire system, if the connection between supply neutral and load neutral is broken, it would result in an unbalanced three-wire star load. The supply star point is isolated from load star point. The potential of the load star point is different from that of supply star point. The result is that load phase voltages is not equal to the supply phase voltage, and they are not only unequal in magnitude but also subtend angles other than 120 degrees with each another. The potential of the load neutral point changes according to changes in the impedances of the phases. That is why sometimes the load neutral also called a floating neutral point. All star-connected unbalanced loads supplied from polyphase systems without a neutral wire have floating point neutral. The phase voltage of the load is not 1 by root 3 of the line voltage in such cases. Then how to solve a star-connected three-wire, three-phase unbalanced load? Different methods are there, and one frequently used method is star delta conversion method. In star delta conversion method, if the given star connected load, this is the star connected unbalanced load, is first converted into equivalent delta connected load, then sold as an unbalanced delta connected system. We have already discussed how to solve unbalanced delta connected system. So here we will first convert the unbalanced three-wire star connected load to equivalent delta connected load. You know how the conversion, about the conversion, ZR, ZY, ZB are the phase impedances of the unbalanced star. Is converted into equivalent delta. These two will be equivalent only if ZRY, ZYB, ZBR satisfies this relations. ZRY should be equal to ZR, ZY, ZY, ZB. ZRY should be equal to ZR, ZY plus ZY, ZB plus ZB, ZR divided by ZB. Similarly, find out the values for ZYB and ZBR also. Then the problem is then solved as an unbalanced delta connected system. The line currents so calculated are equal in magnitude and phase to those taken by the original unbalanced star connected. Now let's move to a problem. This is a given question. A 400 volt three-phase supply feeds an unbalanced three-wire star connected load. The branch impedances of the load are ZR, ZY, ZB are given. Find the line currents and voltage across each phase impedance. Assume R1 phase sequence. Then draw the load, star connected load as per the given values. Then second step is to convert that star connected load to equivalent delta. So first the load is drawn, three-phase unbalanced delta as a star connected load with ZR is 4 plus J8, ZY 3 plus J4, ZY 3 plus J4, ZB 15 plus J20, ZB, this one is ZB 15 plus J20 is drawn. Now we have to convert it into equivalent delta. After conversion, equivalent delta load will appear like this. Now, how is to find out the values for ZRY, ZYB and ZBR. Then Z R Y. Z R Y equal to Z R Z Y plus Z Y Z B plus Z B Z R divided by Z B is equal to let's put ZR, ZY and ZB as substituted. So the equation will become like this and we will get it as 391.95 an angle 113.3 degrees numerator. The denominator is 15 plus J20 is equal to 15.67 angle 60.17 degree. Similarly, we can find out the values for RYB and ZY because YB will be equal to 391.95 angle 113.3. There will be no change in numerator. And in this case, denominator will be 4 plus J8 ZR. ZYB, ZYB is 43.82 angle 49.87 degrees. This much. Then find out inside below. And 1.95 and 13.3 divided by ZY 3 plus J4 will equal to 78.39 and 60.17 degrees. This much. So we got the values for ZRY 15.67 and then angle 60.17. Then ZYB and ZBR impedance values are written in the figure. Then in the question it is given that the phase sequence is RYB. RYB phase sequence. So we are assuming the line voltages RY, VYB and VBR. Then I am 120 degree phase from each other. So VRY magnitude is given as 400. VRY is taken as at an angle 0 degree. VYB will lag it by 120 degree. VBR will lag VRY by 240 degrees. So the voltages, line voltages are taken like this. Now we can find out the values for the currents IRY. The phase currents can be calculated IRY, IYB and IBR. So first let's find out IRY. From the figure we can write IRY equal to VRY divided by ZRY and IYB equal to VYB divided by ZYB and IBR equal to VBR divided by ZBR. Substitute the values for all the voltages and currents. Substitute values for all the voltages and impedances. Then we will get the values for IRY, IYB and IBR. So IRY 60.17 is equal to 25.53 minus 60.17 degree amperes. Similarly, substitute the values for V by B and Z by B. We will get the value for I by B. Final answer for I by B is 9.12 angle minus 169.87 degrees. This much amperes. Then IBR is VBR by ZBR. After calculation, we will get IBR as 5.10 and 59.83 degree amperes. So now we got the phase currents. Now we have to calculate the line currents. Line currents are I1, I2 and I3. And from this diagram we can write the value for I1 as I1 equal to IRY minus IBR. IRY minus IBR. Have the value for IRY 25.53 an angle minus 60.17 minus 5.10 at an angle 59.83 which is equal to 28.43 angle minus 69.1 degree. This is the line current I1. Similarly, we can calculate the values for I2 and I3 also. I2 is I by B minus IRY. Values for I by B and IRY. We got the values. Substitute them. And answer will be like this. Similarly, we can find out I3 also. From this circuit, we can write the expression for I3 as IBR minus IY. Is equal to 13 angle 27.52 degree amperes. So we got the line currents also. I1, this is not I3, this is I2, this is I3. Star connection also I1, I2, I3. I1, I2, I3 in this star connection will be exactly same as I1, I2, I3 in the delta connection. It is clear from the diagram itself. Now we have already calculated the phase currents and line currents. Now we have to find out the voltage drop across each impedances. So voltage drop across ZR is equal to current through ZR, which is I1 into ZR. Current through ZR. This is ZR. Current through ZR is I1. This is ZY. Current through ZY is I2. Okay. We have the values for I1 and ZR. Substitute them. I1 is 28.43 at an angle minus 69.1. ZR is 4 plus J8. After multiplication, we will get it as 254.29 an angle minus 5.67 degrees. This much volts. Similarly, find voltage drop across ZY and ZB. Voltage drop across ZY is I2 ZY. I2 is the current through ZY. that is equal to 149.35 angle minus 170.32 degrees, this much volt. Then we have to find out voltage drop across ZB. Voltage drop across ZB is I3 ZB, which is equal to 325 angle 80.65 degrees volt. So, to summarize, first of all, draw the three-phase, three-wire unbalanced delta connected load as per the given question. Then draw the equivalent delta connected system. Find the values for ZRY, ZYB, ZBR using these equations ZRY, ZY and ZBR. Now analyzing same as that we have done in three-phase unbalanced delta connected system. So the phase currents and line currents are marked. This phase current IRY will be equal to VRY divided by ZRY. And the second phase current IYB equal to VYB divided by ZYB. Similarly, write the expression for IPR also. Then apply KCL to all the three nodes. While applying KCL to this node, we will get the expression for I1 as I1 is equal to IRY minus IPR. Similarly, we will get the equations for I2 after applying KCL here. After applying KCL to this node, we will get the expression for I3 also. Then find out the values for I1, I2 and I3. All the line currents. Then, to calculate the voltage drop across each and every impedances, voltage drop across the impedance will be equal to current through that impedance into Z. Okay, thank you.